Okay, good afternoon, everybody. Before we start, just a couple of practical matters. As I've announced in the morning, the reception will start 5:45, and then you will be divided into the 2x2 groups for the castle tour. The castle tour will be starting at the visitor center, which is just in front of the castle. So please, reconvene there. And we would be very happy to take a group photo right at the beginning of the reception. So if we can meet 5:45 at a probably better if we this talk is just saying after this talk. So better if we just after that talk if we can reconvene and make a group photo inside of the castle. That would be excellent. Okay, that's it. Now, please allow me to introduce Ted Briscoe, who is a professor of computational linguistics at the University of Cambridge, already for a very long time, from what I know. He's been visiting various places elsewhere as well, I think Sydney, Philadelphia, and working at Xerox as well. And Ted has devoted most of his academic career to natural language parsing, which is a field that I'm touching a little as well, and I can say that it's a big fortunate that devoted his aims at parsing were not really as they are in many cases, grabbing another 0.1 points on various data sets like the Wall Street Journal or something like that, but he has really tried to turn his research into practical applications. The most prominent one certainly is the RASP parser, RASP standing for Robust Accurate Statistical Parsing. And the RASP parser is certainly the parser. I would recommend anybody who would like to do English parsing for any serious practical applications. And one of the applications that we'll be talking about now, and that's the collaboration with Cambridge Assessment on automatic assessment of students' essays. And here I hand over to Ted to that.
I'll just use this. I've got a microphone. Thanks very much for that kind introduction. It's a great pleasure to be here. So what I'm going to talk to you about today is a system called Write and Improve, which is out there on the web. And what it's meant to do is help people who are learners of English as a further language improve their writing skills. And what I'm going to try and do is sort of point out that it uses a great deal of lexical information. But interestingly, most of that lexical information isn't the kind of thing that makes it into your standard or even learner's dictionary very often. So it does raise some quite interesting questions for lexicographers. And obviously, we're using only electronic resources like corpora and electronic versions of dictionaries in this work. So without more ado, what is writing assessment? Well, automatically evaluating the proficiency, which can be defined as some kind of grade. What I'm mostly going to talk about today is what's so-called CEFR levels, which are the common European framework description of language attainment. So A1, A2 means you're a beginner, B1, B2 means you're intermediate, and C1, C2 means you're advanced, basically. So the task in terms of scoring a piece of writing might be to assign one of those labels, or it might be to assign an exam-specific score. But perhaps more importantly, from the point of view of a tutoring application to try and improve people's writing, we want to give them some formative feedback. We don't want to just depress them by telling them that they're only A1 or something. We'd also like to give them some hints about how to improve their writing. And we'd like to do all this as well as a human, and in much the same way as a teacher would do it. So that's quite a high goal. Now, the applications of this, it could be used to first mark low-stakes exams. It could be used as a second marking system to check that human examiners haven't gone AWOL and so on. And it could be used in a computer adaptive learning framework where, based on people's performance, you decide which bits of courseware they should look at and so on. And the sort of advantages of doing all this on the, automating all of this is that unlike with human teachers who are harassed and would normally take about a week to turn around a piece of writing and give some feedback, this system takes under a minute to give feedback. And that encourages people to try again based on the cues and, you know, explore things and see what the system does. And potentially the system could be used to profile students, and it's because of the sort of the potential to use it adaptively, so each, depending on the profile of errors people are making, to steer them in different directions in terms of courseware and so on, it can be personalized and you can proceed at your own pace. Okay, so how do we build this thing? Well, we're going to use machine learning techniques combined with computational linguistic techniques. But to use the machine learning techniques I'm going to talk about today are all either supervised, that is, they rely on annotated data, or they're at least weakly supervised. They rely on something a bit more than just raw text. So this is a collaborative project between the university and the press and what is now called Cambridge English Language Assessment. They set 5 million exams in English as a further language last year, and the press sold 3 million textbooks, so this is big business for the university. And for the last 20 years, they've been building something called the Cambridge Learner Corpus, which is exactly the kind of annotated data we need to get started, because these are transcribed scripts in answer to the writing task in exams with grades, and they've been error-coded. And there's a whole load of different exams in there, and most of the exams are correlated with these, or benchmarked against these so-called CEFR levels, which aren't exam-specific. So here's just an example of an error-coded script. The errors are in red and the corrections are in green, and essentially, if you're given something like this, you can turn out sentences which are either the incorrect form or the corrected form, and you can pair them, and that's very useful. And the errors are typed, so something like FV means the wrong verb form, and RP means preposition, replace preposition, so it's a preposition error. And there's about 80 of these error codes. And this piece of text, I haven't shown that here, would come with some metadata, like it's a particular kind of student taking a particular exam on a particular date, and their grade for this piece of writing was whatever, 20. So the process to form the corpus is that you transcribe, most of these are handwritten, so you have to first of all transcribe accurately what they write, including all the errors. So you get something like this, then some though occurred to me, where occurred is misspelled, and then you do the annotation, and you get the error coding. So here there are 3 errors. There's a replace determiner error, can't remember what SX, it's substitute other, so though, it's fairly clear what's gone on here, missed the T off, but it's because they've hit though, that becomes a substitute other error. And occurred needs an extra R, so that's the verb inflection is wrong. Now, what do we do next? Well, we take this learner corpus and we take the corrected form and the non-corrected form and we parse it with the parser, this parser called RASP. And as you can see, this is an awfully long way from something like Wall Street Journal text. So a parser trained on a highbrow financial newspaper is unlikely to do too well on this. And the parser outputs labels that tell you something about the construction. So here it's saying this is an MP made up of a determiner and a nominal phrase. Here it's saying this is the past form of the verb occur, and so on. Now I'll show you the incorrect version, and you can see the shape of the tree is very different. And up here we have T-frag, which means it hasn't found an overall parse for this sentence. It's treating it as a fragment made up of And essentially, the parser is very liberal. It looks for some sort of interpretation. But these -Rs on the end of these rules here indicate that these are very marked rules that you wouldn't expect to occur very often. So the probability of that parse is much lower. And these are all potential cues that we can use in machine learning. So we've taken a flat piece of text and we've added some structure to it. And this gives us a potential space of possible features that might be discriminative in assigning grades, spotting errors, saying what type of error has occurred, and so forth. So we're going to use this as the input to a machine learning algorithm. Another representation that you can output from the parse, this is actually not a learner sentence, this is just some arbitrary sentence from the BNC I pulled out. This representation is just by lexical dependencies, as in dependency grammar between a head and a dependent, and typed with a grammatical relation. So we've got a bunch of representations of the text like this in addition to the text itself. We can lemmatize the words. We've got part-of-speech labels that are, we hope, accurate in context and so on. And this is our potential feature space. So how can we assign a number, a grade, to an entire text? So what we're trying to do is assess the linguistic competence exemplified by the text. And really what we're doing here is trading off the richness of the text against the number of errors made in the text. And then in order to make this useful, we've got to feed it back in some comprehensible way to a learner. So how do we do this? Well, we use machine learning. So what we're doing is we're training and then predicting. And when we train, we take these examples from the CLC, which have the labels already, they have the grades already, and we extract all sorts of different kinds of features, and we feed these into a learning algorithm that weights these features to optimally correlate with the human grades in the CLC. And then when we've trained that, we have a model, and now we can take unlabeled, ungraded text and feed it through, and the model will assign a grade. And there's various kinds of models that you might use at this point. The two that have been used for this task most frequently are regression, where we treat this as a problem of trying to predict a real number and some distribution of real numbers, so if you like curve fitting and things like that. Or you can treat it as classification, where you have a number of labels which don't stand in any relationship to each other. So we might, for example, think of labels like pass and fail, or good pass, pass, fail, bad fail. But actually, the right way of thinking about this, I think, is it's a ranking task. And there are ranking algorithms which, for example, are used to rank web pages. Because a grade system is a scale, and it has structure. A is better than B, 3 is better than 2, and so on. So what we want is an algorithm that doesn't treat these as reals, but rather ranks things optimally, given the gold standard grading that we've got. So here's what an algorithm that does that kind of looks like. It basically has a bunch of features it extracts, and here I've given you some examples of feature types that you might extract. We'll go into that in more detail in a minute. And it uses what's called pairwise rank preference. So what it's really doing is saying, given this new script, does it look more like a 1 or a 2? If it looks more like a 2, does it look more like a 2 or a 3? And it goes on doing that until, let's say, you then look at whether it's a 3 or a 4, and it looks more like a 3, and you stop at that point. But actually, there's a very efficient way of doing this where you don't have to do it in that stepwise way, but nevertheless, it boils down to that kind of computation. And the way the person who first came out with this algorithm was somebody called Torsten Jochems in 2002, and he defined it precisely for the web page ranking problem. So we've taken essentially that algorithm, and most of the results I'm going to tell you today are about SVMs, although the online version on the web uses a much more efficient machine learning algorithm than SVMs. And so what we're trying to do is learn an optimal ranking algorithm which has low loss on the ranking given by the human examiners. And we need to choose feature types that are going to be discriminative for this task. So obvious sort of features you might use are words and word sequences, or lemmas and lemma sequences. So if you see something like the people is, that's probably indicative of a kind of error. So you might have a negatively correlated weight with getting a high score, for example, for that. We can have part-of-speech sequences of the part of speech of the words in context as extracted by the parser. We can have grammatical constructions in terms of these rule names that come out of the parser, and they kind of generalize over constructions of this sort of type. So these are instances of those kinds of constructions, and so therefore they generalize better over more scripts. And we can have things like an error rate estimate, and the way we do that automatically without the error coding is we essentially use a large n-gram corpus, and if a sequence doesn't occur in that corpus, then we assume that it's an error. And then we just take a ratio of unseen to seen n-grams in a text, and that's our error rate. And you can use things like readability scores, so that there's these algorithms to define how readable a script is and stuff like that. There's a very large space of possible features that you might use. And now, if we have a look at how well we do on this task, the way we're going to measure how well we do is either in terms of Pearson or Spearman correlation. And this measures, if you like, the agreement between the human grades, or the gold standard grades, and the machine grades. And if we add these features in this sequence, so if we just do it with word sequences, you can see our correlation is around 0.6. If we add part-of-speech sequences, it goes up quite a chunk. If we add readability scores, metrics, it goes up a bit more. If we add grammatical constructions, it goes up a bit more. And if we add the error rate, a bit more still. And actually, if I replace that with the manually coded error rates in the training data, it gets even better still. So that tells us that our estimate of error rate, there's room for improvement in it. The upper bound isn't 1, so correlation is between 0, no agreement, and 1, perfect agreement. But 2 human examiners don't agree on this task. They usually are around 0.8. And when I say usually, that's actually senior examiners who work for the company, not the kind of people out there in China who are actually marking a lot of this stuff. So God knows what their correlation is. And just to prove to you that ranking is better than regression, here I've compared 2 models, one which is a regression model, using exactly the same feature sets, training set and test set, against our model, and you can see the correlation is really quite significantly higher. So that suggests it's right to treat this as a ranking problem. And just to prove to you that this is pretty good, so in effect, I think indistinguishable from a human, here's 4 humans marked. So our test set is about 100 examples in this experiment, and they've been remarked by 4 senior human examiners and marked by the machine. And your task is to tell me which one is the machine. Anybody like to say? The score range here is 0 to 40, and the pass mark's about 23, and it's an exam that tests whether you're B2. So if you pass, you're B2, an advanced intermediate learner. Anybody like to guess which one it is? It's difficult, right? You know, this is the first 10 examples from our test set. You look at this, that's kind of interesting. That's a big difference. It's actually rater 0 is the machine. And actually, if we didn't have rater 2 in there, maybe 1 or 2 of you might have been brave and guessed that it was rater 0. The system is weaker on outliers because it sees less of those in the training data. So in the training data, about 80% of the scripts are passes. And it's also probably weaker at really good stuff like this. Okay, 3 of them say this is high. This again, the system again correlates quite well with rater 2, who's obviously a bit meaner. That may be because it's kind of conservative around the edges because it hasn't seen stuff like that. So what sort of features? So I told you about the feature types, but here's some instances of those features. So it turns out amongst constructions in this exam, using adjectival or adverbial phrases is a really good way to score well. And that's, you know, you're using more enriched language if you say, you know, the clever person rather than the person or something. And producing things that the parser can't parse is really bad, not surprisingly. Actually, the most discriminative feature in the whole thing is error rate. And if you look down these, most of these features are actually positive rather than negative. And there's over 100,000 instances of these feature types in the system. So, error rate is essentially, you could think of it as taking all sorts of little cues about positive performance and really comparing those to one or two features like this t-frag feature and the error rate. And that's how it works. And it's kind of, probably doesn't really work how an examiner works, but it's still quite difficult to sort of figure out what you would have to do to beat this system, because there's 100,000 of these things in it, in this particular instance, roughly. Okay, so how do we display this to a user in a useful way? Well, we just have a scale which goes from A2 to C1. We haven't really trained. A1, they write so little that you can't really train on that. And C2, they're near native, so the system's really not appropriate to people who are C2. And, you can write a bit of text, and it's coloring the text green. I'll talk about that in a minute. But essentially, if you were to then retype some more or change this a bit or something, your latest score might improve over your previous score, and that might encourage you to keep trying and keep resubmitting the text. Okay, here's a much better, I just put another script in here, which is a bit longer and so on. As you can see, it's just jumped up because there's a bit more text there, and it's all quite good. It's all green. Okay, so that's the summative score, but if you get a bad score, as I say, what do you do next? You need a bit more help. So we want to give word-level feedback and on errors, and also make at least some suggestions about how they might be corrected. Note that we don't want to tell people what the right answer is. There are systems out there on the web that purport to tell you what you should have written. Most famously, of course, Word, which is incredibly irritating because it very rarely gets it right. And if you think about it, it's very hard to tell people what they should have written, because in the limit, you need to know what they intended to say, which is well beyond the capabilities of current computers. So we're trying to do something a bit different. We're trying to give people cues that get them thinking. This is pedagogical. It's meant to help you learn, meant to make you think, not tell you the answer. So the way we do this is we derive rules from the corpus, and we essentially use sort of sequential-like rules based on the error part of the corpus. And we're very conservative about these rules. So we have to see these rules a lot, or these sequences a lot, as errors before we feel brave enough to make suggestions based on them. And we also use a dictionary to get rules about morphology and things like, inflectional problems, like the occurred example and so on. And we get a precision of about 90%. That is, we only say things are wrong when they're right in about 10% of cases. But a very low recall, we only spot about 10% of errors, so we're missing about 90% of the stuff. And the reason to do that is because you can show that there's a really big effect on learning rate if you keep telling people that things that are right are wrong. That's a bad thing to do. And actually, if you look at what teachers do, teachers very rarely correct everything in these scripts. They're often doing it for 40 people in a class, 5 or 6 times a week. So they tend to pick salient things and just correct a subset. So the system, to some extent, mimics that. We've made a virtue out of necessity there. So this is how the rules work. You have in the corpus something like he want to. It says it's a verbal agreement error, and the correction is wants. So if we see that exact sequence, then we will suggest that as a correction. And some are based on unigrams because they're just inherent word-level errors. Some, the context, a bigram is enough. And we learn all the rules like that that are sufficiently evidenced in the corpus. So if you just see this once, that's not enough to learn this rule. And what does that look like in the system? Well, you can select error feedback in the system, and you get red boxes around words. So for and etc, it says and insertion. You may not need and. For etc, it says substitution. A different word might be better here, so on. So if you actually took our and put so on, it would still be wrong. You need to think, right? You need to think about how to make that into a piece of OK English. With C the C, where I've just switched the spelling of C here, when you correct this, it stopped telling, when you correct this, it stops telling you that the is a problem. So if you iterate round on this and you do a bit of thinking, eventually, you will get there. But this is not kind of giving you the answer. Okay, so that only covers a very small subset of the errors, and we'd still like to focus people on what we think are the errorful bits of their text. So what can we do? Well, we can try to take sentences and assign a grade to a sentence, but there we can't use supervised learning because we don't have grades for sentences. All we have is error-coded sentences and an overall grade for the text. So here we use a sort of weakly supervised trick to try to infer a kind of grading for a sentence and train a system based on that. And we also use a different set of features, so it turns out that different features are optimal at the sentence level than at the whole passage level. So this is a completely different model. I won't take you through all the features. But this is the kind of thing it does. So the top are the corrected versions of these sentences. These are real sentences from the corpus. And as you can see, the top ones are graded higher because they're all greener than the lower ones, which are either orange or red. So that's a sort of anecdotal evidence that the thing is doing the right sort of thing. So typically in your essay, you might see something like this. There's a couple of things that you need to focus on here where it's going to make some specific suggestions. It doesn't like this sentence at all because it's ungrammatical, and it's also able to make some specific suggestions there. But if it wasn't, it would at least say this is red and you should think about it. And then you're encouraged to try again and resubmit. Okay, so is this a good system? Well, we did some user trials on some real learners, and I won't talk you through this in a huge amount of detail, but basically, very rapidly, they put in 500,000 words of text, so they actually liked it. They weren't coerced to do this. They wrote quite longish essays. The average number of revisions was about 3.2, but one guy put in 54 revisions. He was Chinese, very enthusiastic. But the really key thing for us was that in over 80% of cases, the revisions that people made actually improved their score. So that suggests that the cues are kind of good enough that they are able to improve what they're doing based on what we can automatically tell them about what's wrong with their text. So that's sort of very promising. And then we asked them a bunch of questions, and in the first trial, they hated the user interface. So in the second trial, we changed the user interface, and the numbers go up. This is a scale from 0 to 5, where 5 is we really like it. And basically, this is a fairly positive kind of trial. So that's good. This is the first version which was built with no kind of UI expertise or anything like that. None of us know how to do this kind of stuff. But these days, we work with people who do. And then we asked them to give comments. So the first comment, both these comments are real learners, as you can tell, and they forgot to put their comments through Write and Improve, so they're slightly dodgy English. So the first guy says, I like it that it's fast. So typically, with his teacher, he'd be waiting a week for any kind of feedback. And second guy says, the coloring system's great, but I really wish you'd just tell me the answer, which is what all learners say. Okay, so that was a non-exam specific version. What I'm going to do is just take you through very quickly an exam specific version and show you what happens when you take a particular exam. So this is IELTS, which is the sort of jewel in the crown for Cambridge assessment. Last year they marked 2.5 million of these things. This is a high-stake test which gets you into a top, English language university. So I think in China there's about 500,000 candidates a year, for example, for IELTS. And in IELTS, you get a score between 0 and 9, and it's essentially saying, are you somewhere between about A2 and C2? So it's looking at the sort of top 2/3 of the CFR level. And to get into a good university, you'd need at least a 6.5 or something, which is supposed to be about lower C1 or something. And the writing task is scored along these different dimensions, and all you see as the learner or the candidate, you just see the final holistic mark. But examiners are supposed to mark on these kinds of dimensions, like did you use good words? Is the thing organized well as a piece of text? Have you actually answered the prompt, task achievement, and grammatical range and accuracy, which, as you can see, is mostly what Write and Improve looks at the moment. And they're typically producing either 150 or 250 words, because there's 2 writing tasks. And the 150-word one is often something like, here's a graph, talk about what this graph tells you. And the other task is usually an argumentative thing, is sustainable energy, sustainable, or something like that. Okay, so let me just tell you what's actually involved in building a thing like this. Really, the model stays the same, but the features change quite a bit. So in the first model I told you about, that was really based on an exam called FCE. We had these feature types. So we also have lexical sequences in the IELTS model, but with POS sequences, we actually found that the distribution of the POS types was very important. So, use of pronouns, use of numbers, particular kinds of lexical verbs, so particular forms of verbs, particularly the passive, I think, is quite discriminative. Passive participle. Locative nouns, that's because you're describing locations in graphs and things like this if you're doing this task well. So you get, you can sort of see that the task in the exam is actually defining what features are discriminative. So we have to rebuild the model if it's going to work well for IELTS. It turns out that not just the rule names, but also these grammatical relations matter a lot. And if you look at the ones that are really discriminative, it's ones that are selecting for more complex constructions. So C subject means you're producing a clausal subject to a verb like be. Something like his getting the prize was irritating. That's quite complex language. Object 2 means you're producing something like a ditransitive construction. X mod means you're producing modifiers which are unsaturated, like, the person, who to talk to or something like that, some sort of relative construction. So, these are indicative of more complex language. Word and sentence length, number of unique words, so vocabulary size matters more in IELTS to get the high scores. Discourse connectives, because discourse organization is a big part of getting a high score here. And we do this in a very sort of trivial way because we just have lists of words that are good kind of rhetorical, they cue various kinds of rhetorical relations between sentences. So not a very sophisticated discourse model, but nevertheless, these are the features, and these are the words that trigger that feature, and these features are pretty discriminative. So distribution of errors. In the previous system, we looked at the 80 error types, and none of them were more discriminative than just an error rate. But for IELTS, it turns out that specific kinds of errors are much more discriminative than other types of errors. So by the time you're an IELTS candidate, if you spell something wrong every now and then, the examiner pretty much ignores it. But there are certain kinds of errors that will really lower your grade. So it's better to look at error types independently rather than an overall error rate. Okay, so then you build the system based on that after lots of experimentation, and we get pretty good correlation, not only on the aggregate grade, but also on all dimensions. So this is the upper bound, and these are the system scores, one on top of the other. And you can see that it's, if anything, better than the more general model. What's very interesting, though, is that to get this correlation here, here, and here, you might think that you'd need slightly different features because the examiners would be scoring based on different kinds of information. But actually, you just use the same feature sets, but they get weighted slightly differently to get optimal scores. So what that tells you is that examiners find it very difficult to evaluate coherence and cohesion independently of things like grammatical errors and sort of whether you've addressed the task and this sort of thing. So actually, although maybe this does help them think a bit about what the overall score should be, these numbers that they produce for these different dimensions are not purely assessing these dimensions. So you can use tools like this to figure out, to some extent, what examiners are doing. Okay, if you were going to use this system, you know, in a sort of more serious context, you would probably want to try to stop people just submitting any old text to it. We're quite good at dealing with things like garbled sentences, but where we don't do too well is flipping around of sentences, because there's not much in this model that really assesses whether you've got a well-organized piece of discourse. Even in that IELTS model I showed you, you're just looking for these kind of keywords that suggest there's some kind of logical structure to the discourse. So if we jumbled up those and we had additionally at the start of the whole piece of text, the system wouldn't really spot that. So you can see that, because if you put in text that you have manipulated in this kind of way, and which you've got human examiners to grade, what you find is that the correlation for randomly ordered sentences is incredibly poor, even though the system's pretty good at spotting just word salad and things like that. So you want to cheat at this system, just learn a whole bunch of sentences that are really good bits of English and contain lots of additionallys and furthermores and so on, and spit them out. So what can we do to stop that? Well, what we built, there's lots of things you can do, but this is the one that turned out to work best. It's likely that you should not only do this. You can think about discourse as being organized at a global level and at a local level. At a local level, does one sentence exhibit semantic similarity to the next sentence? That's local discourse coherence. You can measure semantic similarity by essentially building a vector, a distributional vector for a word. So this is distributional semantics. And you take all the context vectors for all the words in one sentence, all the content words, and you compare them to the context vectors for all the content words in the second sentence. And basically that gives you a measure of local coherence. So if you randomly jumble up things that are really, you know, not related to each other, this score should come out lower than if you produce something which is coherent. And again, that's nothing like what a human examiner does, but turns out that you then improve your correlation on randomly ordered sentences quite a bit. So this ISA just stands for incremental semantic analysis, which is the distributional semantic model that we use. And overall on our test set that now includes about half the examples of these kind of randomly permuted things, we're still getting a pretty good score now. So we're correlating with what human examiners think about those texts, those outlier texts as well, fairly well. Okay, so far so good. But what happens when you're an irritating journalist and you start doing things like finding systems like this online and putting random text through them? So the Educational Testing Service in the US has an online version of something like this, which doesn't work nearly as well as ours because it uses regression. But somebody stuck Churchill's famous speech that we shall fight them on the beaches, we shall fight them on the landing grounds, and so on, through this, because he thought, this is brilliant English, you know. And the ETS system said it was absolutely crap English. And surprise, surprise, our system says it's not completely crap, but it's, you know, Churchill's about B1 or something. Okay, so, you know, and you can see there's a lot of red in here. And if you read the red bits, they are actually rather long, complex sentences. And probably in the training data for this system, you don't see words like Gestapo. And typically, the sentences aren't 30 words long. And the other thing is, this was picked out of Wikipedia. It was actually a speech. And this is a poor transcription of that speech from Wikipedia, which is not punctuated very well at all. If you listen to Churchill recorded saying this, it doesn't, you know, come out like he's producing a huge, great long sentence rather monotonically. So there's lots of things going on here. But the one thing that you can say about these systems they're as good as their training data. So you put something into them which is very unrepresentative, and they don't know what to do with it. It makes them very different from people. So, you know, it's very unlikely a learner would put something like this into a system, because it's very unlikely a learner would ever produce this unless they came, you know, through in a time machine or something, I don't know. So I don't think that that's actually a very useful way of thinking about what these things do. But it does highlight that these things are not replacements for teachers or something. Okay, so what can we do to make this thing better? So it's actually pretty good at telling you what your performance level is. But what it's bad at telling you is, you know, all about the errors you've made. So the only way of getting that better that we've come up with at the moment is just to annotate a lot more data. So we've got 40 million words of error annotated data. I reckon we need probably 1 billion words of learner data annotated before we would start to asymptote in terms of performance. So we actually have a program to annotate a lot of this stuff, and we're actively seeking people who would like to earn money doing this. We have an online distributed system where you can do this. This is the annotator. You can see what the annotator's not completely stupid, because it's coloring the stuff that it thinks need annotating based on our current model. So we only annotate stuff that we don't know about. So it's saying, it's not necessarily saying all this stuff in black is okay. It's saying, I know with some confidence about errors in that, but I don't know about Puerto Rico, how to spell that, and I don't know whether through is correct here. So it's actually guiding the annotator to annotate things that we don't know about. And that's going to be a really Sisyphean task, but the magic of crowdsourcing and so on will make it less Sisyphean for any one individual. So anybody who's interested in doing some annotation, do get in touch, because we're actively seeking people. The other thing that we want to do is introduce more conventional lexical information in this, because if you've been listening as I went along, virtually all the features that we use are lexically specific features. You know, they're features of this word's part of speech in this context, things like that. So it's all lexical, this. And where we can't give very good suggestions, but we know that something's errorful, it makes sense to show people the learner's dictionary entry for it. And of course, to do that, we need to use the sort of techniques that were talked about earlier this afternoon in this room, where we link word senses to errorful words by using something like Lexical algorithm or something a bit more sophisticated. So we do an automated intelligent dictionary access. So here's an error. Electricity allows to travel without carbon producers. The error I'm interested in is that allows has been produced with the wrong subcategorization frame, the wrong kind of context. We need a us here. And actually, the current system does tell you that, because it's such a well-known error. It actually says, is something missing? Do you mean to put in us or something like that? But there are many errors of this kind that we just don't pick up because they're quite complex. The learner's dictionary does tell you quite a bit about valency frames for verbs. So if we were able to pull out the right sense and just display it as a pop-up box, again, that would be a clue to people. So we can spot, you know, that these things are wrong quite frequently, but we can't, you know, make a sensible suggestion. So adding in the dictionary is a good idea. Okay, so now just to sum up, we've got to the point where we're pretty indistinguishable from a human on grading. We have figured out how to visualize some of this stuff so that a learner can interpret it, but actually that's an ongoing thing, and the design of the UI is always something that everybody has an opinion about and wants to change every day. So one of the things that you might have spotted about this one is it relies on red and green, and that's bad if you're colorblind. So every time you talk to a visualization guy, they have a fit, you know. And we want to keep doing user-based evaluations, and you know what we try to do nowadays is do analytics on what people are doing on the web. So rather than doing the sort of experiment I told you about before. But we do know that the thing is kind of useful on the basis of what we've done already. we've covered a lot of the exams. So I gave you IELTS as an example, but we've covered a lot of the other exams. And we can give feedback at various levels, at the text level, the sentence level, and the word level. And we're about to add prompt relevance. So we're about to actually add something which looks at the prompt and content words in the prompt and says, is this an answer to the prompt? And it works somewhat similarly to the local coherence model that I showed you. And we also would like to give some feedback on discourse organization, but that's kind of quite complicated, because how do you tell somebody in an intuitive way who's not a linguist and not necessarily very sophisticated about language, or indeed maybe about computer interfaces, that, you know, this sentence doesn't quite fit here? So that's a challenge. And there's a lot we could do which was L1 specific, because a lot of errors are quite L1 specific. So that's potentially a direction we might go in. But the big problem is errors, because there's a massive tail of errors that we really can't kind of tackle. There's lots of combinations of content words that are not quite right. So a very frequent one is overuse of familiar adjectives like big. So if you talk about a big conversation, that's not quite right in English. But then you have to think, well, do they mean a long conversation or an important conversation? And trying to figure out the right correction in context is really beyond the current technology. But maybe popping up something which says, here's some synonyms and hyponyms, and maybe one of these would fit better, and here's some examples from a dictionary, isn't beyond the current technology. So I think I've pretty much finished. And if you want to see a nice video about Cambridge English Write and Improve, then just type this into the web. And if you want to be an annotator, send me some text, so an email. We pay incredibly well. Okay, thanks for listening.
Thank you for a very nice questions. Oh, yeah.
Yeah, I'm really interested in this bit about content word error detection and correction. And it's true that you can spot things like big conversation and they look like errors because they're very improbable. But what's actually very powerful is to be able to determine the correction. And if you can determine the correction, that actually makes the error much more likely, because you can have all sorts of really improbable things, you know, like Angela Carter's The Busy Clock Carved the Hours into Sculptures of Ice, where, you know, pretty well every pair of content words has never been put together in that way before. But there's no way that you can improve that by substituting a synonym or something. So can you get your error model to say, this is, you know, this is much worse if you can correct it than if you can't correct it?
Well, first of all, we don't, although I think just about every published paper on this in the literature just basically equates semantic anomaly. So I'd say this is anomalous. It's, you know, it's not just rare, it's anomalous. So you can have rare things that are absolutely fine. So using frequency to spot the cases is actually no good for this. So we do something a bit more sophisticated, although this is not in the public online version at the moment. We actually use a compositional distributional model, and we look at where the composition of the two vectors for the two words puts you in semantic space. And very roughly, if you end up in a very unpopulated semantic space, that's quite a good cue for anomaly. Now, it probably wouldn't deal with Angela Carter, because what's the difference between creativity and anomaly? That's very subtle. But for these learner texts, that is actually quite a reliable cue that there's something wrong. And now the correction, what we do at the moment, at least in the experimental system, is we just look for synonyms of one or other word. And you know, that's partly driven by the fact that we know, for example, that adjectives tend to be over-applied. Frequent adjectives are over-applied. So here we'd focus, first of all, on telling people about synonyms for this. Whether this will make it into the system anytime soon, I don't know, because it doesn't actually meet our criterion of being 80% plus precision. It's very, very hard, this.
But the fact that you can do that with the synonyms and get you into a normal part of the space is what distinguishes you from the Angela Carter case, isn't it?
Yes, because if you substitute long or important, you will end up in a more populated part of the space. So that suggests that it probably is anomalous.
Yeah.
And there is a correction. Figuring out whether it's long or important is virtually impossible. I mean, in some cases, the context just doesn't tell you. If it does, it requires too much inference to really do it reliably with a machine.
Thanks.
I was intrigued by your remark concerning the discourse coherence, and if I remember that correctly, you said you have a minimal coherence tester, and there's enormous literature about connecting connectors and discourse coherence, such as if somebody says on the one hand and then on the other hand is missing. I know that computational linguists are always working about these kind of sequences of these connectors, and I'm wondering if you have given a thought to this idea.
I can't resist telling you this anecdote about my daughter, who used to, when she was about 3 or 4, say on the one hand and on the two hand. And I used to think, my God, it must be terrible to grow up with 2 academics as parents. But yes, there's a big literature, and there's a big computational linguistics literature too, but actually turning that into practical automated techniques is pretty hard. We've only really scratched the surface of this. I do know the literature, but the things that we've tried are, they're essentially at the very kind of coarse-grained end of it. One of the things that I'd like to understand before I do much more work on, you can incorporate that stuff into the grade you give, and you can show that it improves the accuracy very slightly. It's how to give feedback, which is, really difficult, I think, because yes, you can start writing lots of linguistic kind of gobbledygook or something if you spot something like on the two hand, but or maybe that one's easy, but you know what I mean, but how you get that over to a learner, I'm not sure. One of the things though about this system is that, there's 1 billion people trying to learn English, and it's predicted to go up to 2 billion by about 2050. And in China, for example, most people are not taught by a native English speaker. They're taught by somebody whose their own English attainment is probably only upper intermediate. So those people are not stupid, and they can talk about discourse organization and essay organization, because that's not very language specific. But where they fall down is on, the language specific stuff, the code. So in some ways, this actually complements what teachers can do worldwide, on average, quite well, because it's good on the coding end of it and not so good on the other end of it, which is less language specific. So we're not promoting this as some kind of replacement for teachers, although every time I give this talk in front of EFL teachers, that's what they think. First of all, the first response is it doesn't work. You convince them it does work. They then say, okay, so you're going to try and replace me. That's not at all what I think about this stuff. I just don't think it's anywhere near good enough. But what I do think is it can compensate for that kind of issue, that if you're in China, you're very unlikely to have access to somebody who could tell you how to produce a clausal subject, with the verb be or something. And, even for teachers who could, they're often teaching so many people that this can make them effectively more productive by taking some of the dross work, correcting the spelling of accommodation again, out of it. So it is a real challenge, and I don't think we're likely to solve it anytime soon, but it may be that for practical purposes, that's actually not so critical.
Any other questions?
If I understood correctly, now you use some kind of rule-based mechanism to find the errors, the error types. Based
Not always
on
rule-based, actually. I mean,
Okay.
we do have a machine learning
I was wondering,
model.
Are you seeing that as a labeling task, like for conditional random fields, something like that?
Well, it's not. We don't use conditional random fields, but we do have a model that it's basically a perceptron model, which basically says this word's errorful or not. And then we just put we put a dashed box around it because we don't have a suggestion about the correction, but we do think it's an error. Where we put a solid red box around a word, that's actually rule-driven. The rules are automatically derived from the corpus, but where we're suggesting a correction, it's based on these sequences that we've pulled out that are coded as errors in the corpus. So that's not really much machine learning in that bit.
Okay.
But we do actually have a word error model, which is the machine learning model.
Yeah, but you could see it as a label. I mean, identifying the error types, you could see it as
well,
a labeling
people have
task.
treated, I mean, we also have participated in this thing. There's a shared task on grammatical error correction, which we won last time. And in that, we were using multi-class models and things like that to predict errors of different types and so on. But, the problem with all of that is, machine learning is great at generalizing, but that usually means that your precision goes down to the point where for a learner it's not really so helpful. So it's difficult.
Thank you very much for your very interesting talk. I have two small questions, if I may. The first one is there any way in which the system deals with avoidance? Because it looks at what's there. Can it look at what's not there, what learners have avoided writing? That's question one. And question two, can you think of ways of customizing the system for certain tests? For example, I'm thinking of the IELTS, the first part of the IELTS test, which asks the candidates to look at a certain graph, and can you include in the system certain keywords from that graph or table which need to be mentioned in the essay or something like that?
Well, that's the beauty of machine learning. If you have some answers, if you have enough answers to those kinds of questions, and you've got the grades, the machine just figures that out, because we just define this huge space of possible features, and it learns automatically to weight them. So those are features, what you're talking about for us. And we don't have a prior opinion about which words matter and which don't. But it figures it out for itself, and it figures out an awful lot of these rules, which in aggregate, make it very accurate, although each individual little rule, if you like, will only fire, occasionally on specific scripts and so on. That's why, for example, on IELTS, it's looking for locative nouns, because locative nouns are very important in describing what's going on a graph. You're really describing a picture in some sense. So they're saying things like, in the top left-hand corner or something like that. And that's locative. So we didn't tell it to look for that. It figures that out for itself, just given the pars and the script and the score. It can tell the difference between features that get you a high score and a low score. Now, the model we built actually just generalizes over the two writing tasks, but it's probably the case that we could get possibly an even better model that, you apply just to the first writing task. So it's all about training models on specific sets of data. And there is some work in that, there is some manual work in that, because we still specify what feature types to look at, but we don't tell it what feature instances matter. So, the features you suggested are all just lexical features. So they all just fall into word sequences of 1, 2, or 3 words. That's a huge potential feature space in which a certain set of words will turn out to be very discriminative and will therefore get highly weighted. So, used to think about computational linguistics as all being about an expert thinking of rules. But now we think about it as we've got data, which is labeled, and the system figures out the rules.
On one of your slides concerning the correction of trigrams, digrams, and unigrams, there was an example that showed singed would be corrected by sang. But what if it were just a typo for signed? Does it mean that, for instance, the phrase he's saying the document would be considered as a correct phrase, and on the other hand, would it be possible to add more information to distinguish between those two kinds of errors?
Which one are we talking about?
Yeah, at the bottom, singed and sang.
Well, it's coded enough times in the corpus as an error of that type that we just learned that rule. We're not thinking about it. We're running an algorithm that says over 90% of the time, when we've seen this in the corpus, it's been corrected to that. So we assume that it isn't really contextually dependent. But we could get these things wrong, and we're not doing anything clever. Short answer.
Okay, thank you.
Okay. Ted, thank you very much once again for an excellent talk.